again. It's as Joel mentioned, it's great to actually get a second chance at these things. Um, so this talk really is to try and share some of my experiences, basically working in the Andean belt, South America. And of course, these may be quite distinct from what you find in different exploration terrains, but I hope there's some commonalities that are of interest and application. So the Andean belt, moving quickly into this, is a mountain range that extends about 9,000 kilometers along the western continental margin of South America, which is convergent with the Nazca Plate. That Nazca Plate's been subducting beneath the South American continent in a fairly continuous manner for about the last 170 million years, and has been accompanied by volcanism and the emplacement of intrusive rocks, and of special importance, the development of copper mineral systems along an arc or belt of about 5,000 kilometers or so of the Andes, extending through the northern half of Chile and Argentina, on through Peru, through Ecuador, and right up into Colombia. Now, within this belt, Chile is a tremendously prolific copper producer, produces around about 5 million tons of the metal being mined every year, responds to about 23% of the world's production. If you combine that with Peru, the neighboring country, that reaches about 35% of its production. Similarly, on the right-hand panel there, looking at reserves, if we put Chile, Peru, and Argentina together, they ostensibly hold somewhere just over a third of the world's copper reserves. So, although along this whole belt here, there is exploration for other commodities. Lithium's been one that's come into the forefront fairly recently, and gold, of course. Copper here really is king. As I mentioned, much of this copper and the expectation for major discovery is in giant porphyry copper systems, which like Escondida, Collahuasi, Andina, Chuquicamata, Toquepala in Peru. These have very large footprints, often of several square kilometers and even well over 10 square kilometers. So they're very, very large systems, and they're characterized by extensive halos of alteration with disseminated pyrite around their copper-rich nucleus as a general rule. When the entire system is preserved, as shown in the schematic lifted from Silito's type model, high-level epithermal environments may be encountered broadly overlying the porphyry, which will be down at depth, although, of course, erosion may have eliminated a lot of this upper architecture and left the copper-rich hypogene parts of the system at shallower depths beneath the surface. I must say, well, copper-rich, but to be perfectly honest, these systems are often quite low-grade, and so to be economic, they need to be really huge. So for the purposes of geophysical exploration, perhaps the most important characteristics is, in a general sense, of the known Andean world-class porphyry copper deposits is the presence of extensive zones or halos of disseminated pyrite, an often greater connectivity of sulfide grains in the nucleus with an increased proportion of copper sulfides, and they're necessarily very large size. So in the photo on the right-hand side, it's a photograph of the pit at Chuquicamata in the north of Chile. And it's very hard to really get any feel for the dimensions of this thing, but it's about 5 kilometers long, about 3 kilometers wide, and over 1 kilometer deep. So anyway, I mean, there are an infinite number of variations on these themes, but these broad considerations are useful in working out how to go about exploring for these. The disseminated pyrite in these systems, and to a lesser extent, many of the copper sulfides, respond well to induced polarization. So this is a line of 300-meter dipole-dipole IP over a North Chile porphyry copper. It was done before the mine before mining commenced. And on the right-hand side, we have the pseudo sections, and on the left, some quite aged 2D inversions of that data. And you can see that there's a fairly broad IP response which extends around the present-day pit. Well, there's a rough picture of the present-day pit that's marked out as a little black line on the left-hand 2D inversion sections. And in the lower panel, you can see that fairly broad IP response, which responds primarily to most of the pyrite in the system, lesser extent copper sulfides. And then within the core of these systems, we get a greater connectivity of the metallic mineral grains, which are often quite conductive. So you can see that the low resistivity anomaly on this line is more restricted than the IP anomaly and more closely associated with the higher grade mineralization that's been extracted to date. So IP and resistivity imaging are definitely useful. What about other techniques? Well, the broad volume of alteration in a productive porphyry copper system will generally have destroyed much of the magnetite that may have been present. And so we may see a magnetic low, perhaps with a smooth magnetic texture. And you may get a magnetization high related to the deeper parts of the core of the potassic alteration in these systems. However, overlying young volcanics with erratic mineral magnetization, late stage barren intrusives, other complicating factors can lead to magnetic signatures which are not readily interpretable. Here you can see that the case of the Spence porphyry copper deposit and the Sierra Gorda, which lie fairly close together on this with this overlying RTP image from an airborne magnetic survey. Yes, there is a kind of magnetic response to these systems, but you really need to know that they're there to be able to see it, to be able to pick it. So it definitely has a use, but it can be quite difficult to use it as a primary exploration tool. Direct detection with gravity tends to also be very tricky. Problems with variable cover thicknesses, variable cover densities. Also, obviously, in the Andes, we're dealing with quite significant topographic relief, and that has tended to restrict its application to some extent for this as well, at least on a project or district scale. Radiometrics suffers from the same kinds of troubles faced by geochemistry in trying to sample the geology beneath young transported cover, and seismics work very nicely in Joel's examples there, but it can be very difficult in some hard rock settings and particularly in the environments along the Andean belt. Now, the depth intervals of exploration have been continually increasing, so it's not uncommon to be looking for these copper targets, even one burial, as you can see from this example on Gamma. We'll talk about in a little bit more detail further ahead. Wildcat drilling at these sorts of depths is accompanied by risks and costs that are generally prohibitive. And these young mineral systems, the late Eocene was particularly prolific here, are within this environment that's actively tectonic and has active volcanicity. And that means that there's every probability that very recent alluvial or colluvial sediments and or recent volcanics, and in some places we get these very thick and extensive ignimbritic tuffs, cover the prospective rocks. So considering that IP and resistivity have been the tools of choice, we then start colliding some of the difficulties. Much of the Atacama Desert and the copper-rich north of Chile and extending into the south of Peru is extraordinarily arid, and we get these evaporitic caliche layers, which are extremely challenging for the preparation of adequate electrical contacts, especially for the injection of current for IP surveys. You can see some pits on the left. It's a bit hard to make out what they are, but they've been dug out with a backhoe. We'd often break the backhoes trying to break through the caliche, so it's particularly difficult. Further down within the cover sequence, we may find ancient groundwater, which is very brackish and forms extensive low resistivity layers, which will overlie the target rocks. And that will tend to mask the responses. It will depress the received signal amplitudes, and for IP particularly be increasing electromagnetic, inductive electromagnetic coupling, which can be very problematical. And if we don't have these sorts of problems, we tend to be up in high altitudes, 4,000, 5,000 meters altitudes, very steep topographic relief, and the altitude and that topographic relief makes it extremely challenging for the crews to work there. So in all of these cases, some of the traditional IP techniques, dipole-dipole, for example, can become very, very challenging. Trying to prepare regular and contacts, and lots of them too, can become very challenging or very expensive at least. and in some of the higher altitude areas, trying to pull out cables in straight lines over rough topography can be difficult or even simply unsafe. But fortunately, we're dealing with very large targets, which often don't have a predefined trend. So acquiring high spatial densities of data along relatively widely spaced lines is, at least on first pass, an inefficient and perhaps even biased manner of exploring for these targets. So a number of years back, many years back really, with this in mind, we and other groups as well dusted off Kennicott's old reconnaissance IP method, or as it became sort of rebranded as vector IP, as it addressed some of these issues. It required very few transmitter or current injection locations for a broad coverage of receiver sites on a spatially unbiased grid layout. The schematic map of the generic vector IP survey design shows a fairly broadly spaced 1 kilometer grid of receiver sites, each comprised of an orthogonal pair of E-field dipoles, such that the vector of the in-phase and quadrature, or same things in basically on time domain, can be determined. And they're read usually using a single transmitter bipole, often in the order of 2 kilometers in length, which is located either within or just around the edges of that grid. And for large target footprints, an anomalous hit may be expected, which can then be followed up. The problem with this is that such a sparse setup with so few transmitters actually has a very limited sensitivity, and you can get a feel for this with the Frechet derivative volumetric analysis. In this case, it's sort of showing the depth above which that's reasonably high volumetric sensitivity. What it really means is that we end up with very challenging response patterns that can arise, which relate to the transmitter, normally receiver geometry. And they can be very difficult to adequately resolve, as you can be seen in that example on the right-hand side from the Atlantida porphyry system in Chile, where if we take just 2 transmitted dipoles, providing coverage of the receiver sites on this 1 kilometer by 1 kilometer grid in the eastern and the western parts of the survey area, they give rise to a pattern of chargeability anomalies that actually bears little evident correlation to the actual footprint of the mineral system, which is shown as the semi-transparent white shape. Furthermore, there's actually very limited control on the distribution of the IP or the resistivity parameters as a function of depth. So we don't know where the anomaly is in terms of its depth, and we can also gain little information about the cover thicknesses through a survey area. What is true, though, is if you add some more transmitters, and not particularly very many, you can increase the sensitivity of that volume significantly. So if you actually put in 4 contacts rather than 2, you can get 6 transmitter bipoles work and increase that sensitivity significantly to the point where you can start using 3-dimensional inversion of that IP resistivity data set to constrain much better. So same data set, more transmitters, and now you can see in that bottom right-hand side that we've managed to constrain the location of where that IP anomaly is coming from considerably better, with a much tighter and closely related response to the mineral system itself. The problem with this is obviously if you have to sit at each site with a conventional sort of fashioned receiver and then also acquire data from 6 different transmitter bipoles, the survey starts to go really slowly, especially as we are working in conductive environments and we need to run with very low frequencies. So we decided we really needed a distributed acquisition system, and at the time there wasn't one commercially available. So we developed our own, which went through a first stage of being a GDAS-24, and then we moved it up to the GDAS-32s. So they're these 2-channel 32-bit receivers. And they have very good phase precision all the way up to sample rates of 32 kilohertz, which makes them useful also to acquire MT data. And that's nice because once you've gone to the trouble of putting out all your electric fields for the IP survey, if you add a few induction coils, you can then leave that array out overnight if it's a nice desert environment and nobody's going to bother it, at least. And by the morning, you'll have also acquired nice MT data. So with these kinds of systems, you can then start to cover fairly large areas of ground relatively quickly. Obviously, it depends on the access in an area. This particular project area was up at about 4,000 meters altitude and doesn't have great access through it. But the survey on this 1 kilometer grid of sites covered an area of about 120 square kilometers in just about 3 weeks. Roughly speaking, if we'd have tried to do that with, let's say, a similar sort of 1 kilometer space set of lines of dipole-dipole IP, we'd have ended up with a lot more data. Probably wouldn't have materially changed the overall picture, but it would have probably taken 3 or 4 or maybe even 5 times longer. So there is some benefit. But there is some question perhaps over how much you lose by going to these quite sparse sort of vector IP surveys. And to address that, we can have a look at this example from the Caldera copper project near Vallenar in the north of Chile, where we have a vector IP or multi-transmitter, this sort of sparse 3D IP survey, which uses 2 sets of 6 transmitter bipoles, which are shown in red on that picture on the left, and a grid of receiver sites at 1 kilometer spacings, which are the blue dots, which were acquired with both this multi-transmitter vector IP and MT data also being applied overnight. That grid was actually infilled to 500 meters in the central area where an IP anomaly was identified. And from that, you get this distribution of data that's shown as that in that middle panel by a cloud of chargeability data values in a kind of pseudo 3D plot. Using that same GDAS instrumentation, we also acquired a follow-up line of 200 meter of dipole-dipole IP across the main IP response with a 4 kilometer line that was fully populated with E-field dipoles, and then the transmitter dipoles stepped through it to obtain a bidirectional dipole-dipole data set, hence the reason why there's 2 apparent resistivity and 2 chargeability pseudo-sections in that right-hand picture. Now, the sparse 3D IP data set, so that multi-transmitter vector IP data set, was modeled with a 3D inversion. And from that, we got that isosurface or the shells around the most anomalous IP responses shown in this 3D visualization. The section through there is a 2D inversion of the chargeability from the detailed bidirectional dipole-dipole data set. And they show a very close correlation, but perhaps most relevant is really that the very much higher spatial density data set of the dipole-dipole did really little to benefit any much greater resolution of the anomaly, but at significantly higher cost and slower acquisition times. Now, as I mentioned, having spent time installing E-field dipoles for IP acquisition, it should perhaps be considered a bit of a crime not to leverage these with the installation of induction coils to obtain MT data too. So the resistivity models that we get from MT data are generally much better resolution and also provide greater depth of investigation from those obtained from the DC resistivity data set. And as I mentioned, a low resistivity core within a broader IP envelope can be just the kind of anomaly that we wish to find for these porphyry systems. And that's what we can see here with that ochre-colored low resistivity blob sat at depth within the shell of yellow high IP response, making quite an attractive target. That's yet to be drilled, but it is an attractive target. Now, the problem with using a distributed system like this is we could have, let's say, 20 receiver sites out at any one time acquiring E-field data. But if we try and put induction coils at all those 20 sites, that's a lot of induction coils, and installing them is onerous, and there's also a significant cost involved in having that many induction coils on a project. So, in fact, this MT survey and many that we do with these combined IP and MT surveys is actually read as what we refer to as a sparse MT survey, where not all of the electric field sites have co-located sets of induction coils. Rather, the induction coils are required, the data is acquired synchronously, but spatially subsampled. As the H fields generally much more gently varying as a function of location than the E fields, this will generally provide a result in many settings that's almost as good as a fully sampled MT dataset, but at a significant cost saving. 3D inversion with some algorithms, we've been using RLM 3D through GeoTools, does permit the definition of these sort of inter-Z acquisitions to appropriately invert the data too. To test out a little bit the idea behind doing this, we generated synthetic data for a simplified model of this caldera project based on a buried vertical cylinder of relatively low resistivity within a homogeneous half space using the project's topographic surface. We did this for co-located H fields at all E field sites, and also for extreme cases with just one set of H fields, which would have been at a site directly over the conductor, and also one very distant from the conductor. And interestingly, as you can see on those three pictures on the right-hand side, although there is a slight difference in the tenor and anomaly shapes, in broad sense, the interpretation for drill targeting, at least of a relatively large and simple target like this, would unlikely to be materially changed by taking this shortcut on sparse H field acquisition. So now, although these distributed array systems were originally designed for fairly large sort of and broadly spaced sparse surveys, they really can be just put to use on any kind of IP array. So in this example from the Altar project in the San Juan province of Argentina, receiver dipoles were strung along drill roads and accessible ridgelines to form a network of receivers, and then transmitter poles were then stepped along parts of this network, injecting current to provide a messy but very serviceable 3D IP survey. And then with some induction coils installed within the area, MT data was also acquired overnight. And in the case of these, very steep topographic areas, this again was up at around 4,000 meters elevation, 13,000 feet for anybody who works in those units. This kind of acquisition is really the only way to be able to do it. If you try and work on the very steep slopes, they're covered in scree, you get terrible contacts, they can be quite dangerous to work on, and certainly very slow and laborious. So that 3D coverage, when we threw it all into 3D inversion, provides a nice, large, very large, about 8 kilometer sized anomaly, which extends over the whole width of this mineral system. And the anomaly intensities generally do intensify around the areas close to the porphyry centers, which are marked out by these green iso surfaces or shells around the known higher grade copper mineralization. Although it says 0.1%, that's the grades do actually increase significantly higher within those shells. The MT data acquired through leveraging those IP installations with the addition of these sparse orthogonal induction coils, and then simply acquiring time series data for the complete array overnight, provides an alternative imaging of the resistivity to even greater depths, and further confirms, in this case, the excellent correlation of these copper-rich cores to the zones of lower resistivity that lie within that survey area, as you can see marked out here with those iso surfaces. Again, copper shells marked in green, and low resistivities as those warm-colored shells around the lower resistivity parts in this case. And they're not tremendously low resistivity, but they're considerably lower resistivity than the volcanic and intrusive rocks within the environment. By means of another example of a deep porphyry copper system, there was an old historic 200-meter dipole-dipole IP survey over the Valeriano project, identified a zone of anomalous IP response, shown here with those warm colors, which covers an area of about 2 by 2 kilometers. And in plan view, it holds a very neat correlation to the copper-rich nucleus of the system, which is shown here as the green shell around 0.3%. Again, there are much higher grades within that, and that shell's probably a little bit out of date now. I think they've extended the mineralization a little bit since then, but it serves as a general guide. Interestingly, however, if we look at it from the side on, the survey didn't actually really provide enough depth of investigation to actually reach the copper rich part of the system, which starts really from depths of around 600 or 700 meters, depending on quite where we stand on the topic, but it does map the contaminated pyrite in the zone for lytic and ferricitic alteration. We carried out a sparse tensor MT survey, again subsampled or spatially subsampled H-field data used on this, modeled with 3D inversion. And this provides much greater depth of investigation and was very well suited to imaging the low resistivity anomaly associated with the copper-rich mineralization, which, as I mentioned, starts from about 700 meters down and extends to over 2,000 meters now. Restricted depth extent of the conductor obtained from the MT inversion. It was an unconstrained MT inversion, so you can see it forms a blob rather than a cylinder. Is really down to the inherent lack of sensitivity to quite where the bottom of such a feature should be. And so it's no doubt that the data would equally well support a more extensive vertical cylindrical body. Interestingly, the MT data was also able to map out a fairly flat-lying high resistivity zone, more or less overlying the porphyry, which relates to silicification present in the high-level epithermal alteration, where there's appreciable grades of gold. So in summary, I guess what I'm trying to drive at with the talk is that given the specifics of the exploration targets and their settings both geological and geographical, we've tried to find some kind of optimization of the geophysics being used, in this case specifically for these Andean very large porphyry copper systems. So I hope that that's kind of been of interest, and extensions of this approach to other targets, the settings can be thought about, implemented, and help sort of weight this ever fickle odds of discovery in all of our favors. Before I just wind up here, I'd like to extend some thanks to Aldebaran and ATEX and First Quantum for allowing me to show some of the results from surveys we've done for them. And also a big thanks to all of you for hearing me out and for your time and attention.
Thank you very much for that, Jeremy. Really great presentation and really amazing work in very difficult conditions. Okay, we have a question in the chat and from Manish saying, thank you very much, Jeremy. As always, awesome presentation. Have you had any experience of combining ZTEM with your sparse MT in NDs?
No, we haven't actually directly, at least, but I do